discussing about the recursive algorithms. In the last lecture, we have learned how to frame or how to design small recursive algorithms, where mainly we have considered the algorithms which contains some recursive function. Now, today we will see a different type of algorithms. We will continue the discussion on recursive algorithms only, but today we will consider different type of algorithms, not that algorithms containing recursive function. Then also we can write recursive algorithm for our to solve the problems. So, we know that searching is a very important and important technique, where the problem is that we have a n number of elements and n number of unordered elements we considered. Unordered elements, say A1, A2, A3 up to An, and given element is x. So, one element to be searched or a given element is x. Now, the problem is that searching, the problem is that we have to search or we have to find out whether x is in this list or not, this within this A1 to n elements. So, linear search, what we do, what is the approach? The linear search, that we compare x with each element of the list starting from A1, A2, An, and if so, we compare x with each of the element of the list A1 to An. Now, if at the, that means x is compared to A1, then if not, then if it is not equal, then x is compared to A2. In this way, we will go to at the ith state, we will compare x with Ai. Now, if it is equal, then if x is equal to Ai, then I is the location where I is the location of x. So, this is the positive search, x exist in the list. But if x is not equal to y, if x not equal to Ai, then we increase the index of the list which is I least by 1. That means I becomes I plus 1. And we will compare, and we compare x with a I plus 1, and then again we will continue that whether x equal to a I plus 1 or not, and the same thing will go. So, this is our approach of linear search. So, this is my linear search approach. Now, see here there is no mathematical function involved. What last lecture we have discussed, mainly the factorial n, or to find out the GCD, or to find out the power a to the power n, where the algorithm contains the one recursive function. So, here no mathematical function is there, but this we can write this approach or this algorithm, we can write a recursive algorithm to solve this problem of linear search. So, we write the function of linear search. We give the name that say lin search. The function name is lin search, and the inputs are I j x, where I j x are integers. Here I j are the index of the list, or the indices of the list, and x is the element to be searched. Now, if a I at the ith stage, so a I equal to x, then we can write that location is I. Else if a I not equal to x, then we will compare the two indices. That means, if I equal to j, that means my full list is already compared, and then we do not get the element x in the list. So, we can write that location equal to 0. Else we can write that my lin search I plus 1 j x. So, this is my recursive step. This is my recursive step. See that my function is lin search and the inputs are I j x, and if it is not equal to a I, then I have increased my index I plus 1 and j. So, actually this is smaller number of inputs, the way we have defined the recursive algorithm, and then we call the same function. That means, the function invokes itself with smaller inputs. So, this is the recursive function of lin search. the linear search. Okay. So, we can easily we can write the linear search algorithm. Now, if we consider the binary search, then we can write the binary search. So, quickly we see that what is the approach. What is our approach? See, again we have a list of n elements, but in this case the elements are ordered list. So, inputs are here, the inputs is a ordered list, that means it is a sorted array or sorted list, ordered list of n elements. So, ordered list of n elements, and we write this is A1, A2, A3 up to n. Now, here we find a middle element, find the middle element as a mid equal to floor, or first we see the mid location and then we will get the. So, we see first the location, the middle. So, it is I plus j by 2, where I and j are the minimum and maximum index of the list. Indices of the list, and this is a floor function. We normally defined, say floor n is the greatest integer less than or equal to n. So, if it is ceiling 7, then it is equal to 7, but if it is ceiling 7 by 2, so it is 3.5. Sorry. So, this is a floor 7 by 2. So, this becomes greatest integer less than or equal to n, here n equal to 3.5. So, this becomes 3. So, I get a mid is a integer. So, that I get a mid is a integer value, and now I can find the middle element as the a mid. Then I will search, or I will shorten my list. First I will compare x, if x is the element to be searched, then I will compare x with a mid. Now, if x equal to a mid, then my location is mid, then location is mid, that means I got the element x exists in the list. If x not equal to a mid and we get x less than emit, since my input list is a sorted, that means my x, if it lies, then it must be within the first half of the list. That means, now if I consider this is A1, A2, A3, now I got a emit I have computed and then an. So, if x less than emit, that means x must lie between the first half. So, x lies here, x lies here if it exists in the list. That means, if when x less than emit, and if x not equal to emit and x greater than emit, then if I consider the sorted list like emit, to an, then my this lies in the right half of the list, since it is a sorted. So, this becomes x lies here, that means x greater than emit, x greater than emit. And see, then we will search, if I want to write a procedure, that recursive algorithm, say bin search, I give the procedure, name the bin search, then originally if it is I j x, this is my element, then if it is x less than emit, then, and say my, where my mid is say floor I plus j by 2, then for the first case, when it is less than, I will be, my bin search will be that I. Now, I have shortened the list to be searched as ceiling, sorry, this is a floor function I plus j by 2 x. So, it is for smaller inputs. Now, if x greater than emit, the second case, then my bin search will be, because it is in the right half of the list. So, it becomes floor I plus j by 2 plus 1 and j x. So, what we see, that the way we have defined the recursive algorithm, that the function invokes itself with smaller inputs. Now, we see the size of inputs become lesser. It is first, this is the same function, and the input size here, the original list is actually halved. It is partitioned into 2, and this is my left half, that I, from j it becomes that I plus j by 2. Similarly, when it will be in the right half, when x greater than emit, then this is again the right half, that means mid plus 1, mid is I plus j by 2, floor of that. So, this plus 1 to j x. Again this is the function. So, the function invokes itself with smaller inputs. Only thing here, instead of function, I can write my algorithm. So, this is here I can write the algorithm invokes itself with smaller inputs. So, this is the way the recursive function of binary search we can frame. So, now if we write the binary search algorithm, that we give the name the bin search, and the inputs are same as I, j, x. Only here one thing we must note, that it is a I j are the indices are the minimum and maximum indices of the ordered list, that means sorted in any decreasing in order or in increasing order, the ordered list, and x is the element to be searched. Now, first we have to find out, the mid, the value of mid, the middle value, we give the name as, the variable name as mid, it is floor I plus j by 2. Then we compare that if x is equal to the middle element, which is a mid, then location equal to mid, that means we get the element x in the list, location equal to mid. Else if we give that x less than, that means if it is not equal to a mid, then we search whether x is less than a mid, x is less than a mid, and I less than m, that means whether it is in the first half, I less than mid. Okay. I less than mid. Then I will call bin search, as already we have seen, I with the smaller inputs, that means it will be I mid minus 1, that means my first term, the left term, and x. Else if it is not, if I do not get the element in the first term, then else if we will check that x greater than a mid, that means if x not less than a mid, then x must be a mid greater than a mid, and j greater than mid, that means my right half. Then I will call again bin search, then I will call again bin search with smaller input, but this time it will be mid plus 1, then the index j and x. Else if I even if I do not get any of the comparison is true, that means it is not a mid, it is, I do not get that x less than a mid and I less than mid, or x greater than a mid, then it is the x does not exist in the list, that means location equal to 0. Then I get location equal to 0. So, here also we see that first this is my recursive algorithm with the inputs I j x. If it is not the middle element, then my list where we are searching the x element, the given element x, that we are invoking the same function with the smaller inputs I and mid minus 1. So, this is the smaller inputs, that some smaller inputs, because my j, instead of j we are taking mid minus 1. Similarly, when for the right half we are considering, again this is the smaller inputs. It is the same function we are invoking because it is in the right half. So, I becomes mid plus 1 and j. So, here the j becomes mid minus 1. So, lesser inputs, here I becomes mid plus 1. So, again it is the, so the both the cases the length of the list is reduced to half. So, it becomes the smaller inputs. So, it is a recursive algorithm. Now, we see a different type of recursive algorithms, but again we have learned that as a recursive function we have seen that Fibonacci numbers. We know now the Fibonacci sequence. If we remember that we know the Fibonacci sequence as, say, if I give f0, f1, f2, fn is the up to nth Fibonacci number, where f0 equal to 0, f1 equal to 1, and we can write that fi is fi minus 1 plus fi minus 2. So, it depends on the previous two elements. Now, we can compute or we can write a recursive function for computing the Fibonacci numbers. We see that how we can do that thing. So, we write the function, we give the function name as, say, recfibo. To compute, we give that to compute the Fibonacci numbers recursively. Or I can write to compute the nth Fibonacci number, say, number recursively. And I give the name as, say, recfibo n, because it is nth Fibonacci number. So, if n equal to 0, since I know as the initial condition f0 equal to 0. So, I can write that recfibo 0 equal to 0, it is given. Else if we see whether n equal to 1, then also it is given that recfibo 1 equal to 1. Else, so it is, if it is not, then else we write the recursive step that recfibo n is equal to rec fibo n minus 1 plus rec fibo n minus 2. So, this is my, again this is my recursive step. This is my rec fibo n, this is in my with smaller inputs. So, this is my recursive step. Now, if we see an example, that means if I want to compute F4 or say F5, just if I draw that the way it is computing, we know that F4, the recursive step is F3 and F2. Then when it is F3 is computed, again it is F2 and F1. It is F2 is F1 and F0. Now, since the and see F2 is F1 and F0. See, my F0 and F1 are given, that means we can compute straightforward way. So, these are the things I know, since because F0 equal to 0 is given and F1 equal to 1 is given. Now, but at each stage of this, say like F2 here, F3 here, I need a addition, because it is F2 is F0 plus F1. I know, because my F2 is F0 plus F1. So, for this case I need 1, 2, 3, 4. I need some 4 addition. Now, if I quickly remember the numbers, if I write the numbers, that F0 equal to 0, F1 equal to 1, F2 equal to 2, F3 equal to 3, F4 equal to 5, F5 equal to 8 and so on. Now, see, when we are computing F4, I need to compute F4, we need 4 additions that we can write to compute. That means it this 4 I can write as, say, F4 minus 1, because F4 is 5. F0 is 0, 0, oh sorry, I have this is right wrong, okay, this is this sequence is F0 is 0, F1 is 1, F2 is 0 plus 1, 1, F3 is 2, F4 is 2 plus 1, 3 and F5 is 5 and so on. So, for when we are computing, this becomes F5 minus 1. Okay. So, this becomes, when we are computing, this becomes F5 minus 1 for addition. So, in general we can write to compute Fn, we need Fn plus 1 minus 1 number of additions. If we quickly do for F5, then this becomes F4 F3, F3 F2, F2 F1, F1 F0, here it is F1 F0 this becomes F2 F1 F1 F0. So, here also we see we will stop computing when this becomes F0 or F1 F1 F0. So, in this case I need 1, 2, 3, 4, 5, 6, 7. So, to compute F5 we need 7 additions. That means which is 7 is equal to F6 minus 1 is 8 minus 1 is 7. So, just now what we have seen that to compute Fn recursively, to compute Fn, the Fibonacci number recursively we need Fn plus 1 minus 1 number of additions. Okay. Now, if we write a function where we want to find out the Fibonacci number iteratively, that means to compute Fn iteratively, we need simply n minus 1 addition. So, for n greater than equal to 1, always that f n plus 1 minus 1 is much greater than n minus 1. So, what we conclude from here, that means we conclude that not always the recursive functions are good. That means it is not efficient. So, we can conclude that recursive algorithms are not efficient always, because for this problem of computing Fibonacci number, we see that iterative program is better than the recursive program. But we will use recursive algorithms because many times these are if not only efficient, it is implemented much easier way. That means, we can write the code even if it is not efficient. So, even it is not efficient, many time for some problems it is easy to write the code or to write the algorithms. Not only that, and it can be implemented very easily. Efficient way, although the complexity is not good. So, that is why the recursive algorithm is very important in computer science, and for a set of problems actually only recursive algorithm is the solution. So, we will see that how we can find out this efficiency of the complexity when we write that the recursive algorithm. That means, that analysis of algorithm is much easier when we write a recursive program. When we write a recursive program or recursive algorithm. So, in the next class or next lectures, we will see that how we can using the recursive algorithms, we can do that thing.